Hi, my name is Dmitry Rozplokhas, and I would like to present our paper that studies time complexity aspects of miniKanren programming language and its interleaving search strategy. miniKanren is an embedded language for pure logic programming. It gains popularity recently because it's well suited for relational programming paradigm. In this paradigm, we describe functions as relations between the arguments and the resulting value. This way, we can extract many different behaviors from one function. Let's consider this example of length of miniKanren relation for calculating length that we will use throughout this presentation. It has two arguments, the list and its length, and its body is a goal that describes how they are related. miniKanren has very few primitives for constructing goals, and basically all of them are shown in this example. There are explicit unifications, relational calls, including recursive ones, and they can be combined with conjunctions, disjunctions, and introductions of fresh variables. You can see that it's a simple declarative definition that considers two cases of empty and non-empty lists and performs a recursive call on the tail in the second case. With this relation, we can define queries, and miniKanren will perform a search to find answers. For example, we can specify the list, and miniKanren will calculate its length. Alternatively, we can specify the length, and miniKanren will generate a list of this length. This is, of course, no news for logic programming, and the same can be done in Prolog 2. But miniKanren is actually much more effective for this paradigm in more complicated cases because due to its purity and the specific search strategy. This search strategy is called interleaving search. It was introduced in the early 2000s as a compact monadical interface to capture search in logic programming. It represents the whole search process as the evaluation of a lazy stream. And during the evaluation, the streams for sub-goals are interleaved, thus the name of the search. This search procedure has a number of distinctive properties. Most importantly, it is easier for embedding in functional languages, and so today miniKanren has dozens of different versions for different host languages based on this search strategy. It's also a complete search, meaning that every answer will be found eventually. But it also has some properties that are not so beneficial. For example, the fact that this method of combining streams can lead to surprising performance effects. For example, let's consider this plot that shows running time for the query calculating length that we looked at before. Since it is a simple procedure that traverses the list, we can expect it to have time linearly dependent on the length of a list. And in Prolog, it looks like this. But in the reality of miniKanren, it looks like this, which is obviously superlinear dependency, and actually it is quadratic. If we investigate this example in detail, we can find that the reason for this overhead is the process of identifying the next sub-goal to evaluate during the evaluation of the stream. We call this process scheduling. This example is actually quite surprising and even devastating for many in miniKanren community. So we would like to have ability to explain and predict such effects. Unfortunately, for now, there is no framework for time complexity analysis for programs in miniKanren, and the relational programs are usually evaluated by time measuring for specific instances. There is, of course, a huge body of work in the time complexity analysis for Prolog, but it assumes SLD search strategy, so it would miss this overhead of scheduling. This paper tries to fill this gap. Specifically, we define a formal measure for performance impact of this scheduling process, and we present a semi-automated technique to estimate the complexity of this measure for a given program. We consider a restricted class of programs, but it is wide enough. Let's start with the complexity measures. To analyze the search formally, we rely on the operational semantics on the existing operational semantics for interleaving search. It's a deterministic label transition system whose states are trees representing partially evaluated streams. The leaves are lazy goals that should be forced and executed in some environment, and nodes represent partially evaluated disjunctions and conjunctions. Evaluation is then defined by the path along these transitions, which is called trace. One natural measure for evaluation time is the number of transitions in this trace. However, it's not adequate because some transition may not take constant time. In fact, in every step, what's happening is the navigation to the leftmost leaf in the tree, and swapping of the children for all partial disjunctions for interleaving. This is exactly this navigation is exactly the scheduling. So we suggest another measure for evaluation time that captures scheduling, and we call it scheduling factor. It's defined as sum of all depths of the leftmost branches for all states in the trace. For both these two measures, we derive recursive compositional formulae to calculate them for partial disjunctions and partial conjunctions. Actually, the formula for scheduling factor involves number of transitions, so we need both these measures to estimate scheduling. We derive exact equations, but they are rather cumbersome. So we also cumbersome to be used directly. So we also found some convenient approximations that is sufficient for complexity analysis, and actually they are a key tool for our complexity analysis technique. Let's now move on to the description of this technique. Here is the roadmap of our approach. We take a relation with some arguments marked as input arguments, which will be substituted with ground terms, and we want to find how the time of search depends on these ground terms. To do it, we first go through the body of relation and construct so-called symbolic scheme, which shows how the search goes inside the body of the relation. The way to do it is symbolic execution, And since miniKanren is symbolic in nature already, we can, to a great extent, just repeat the ordinary execution of miniKanren, but we need to distinguish some logic variables as symbolic, or as we call them, grounded, to denote that they will be substituted with ground values. And we need to check carefully how these ground values affect the flow of the search. From the symbolic scheme, to the symbolic scheme, we can apply the compositional formulae from the previous slide that I mentioned in the previous slide, and extract recursive approximations for this relation that relates measures for initial relational call and measures for internal relational calls in the body. Finally, we need to solve the system of recursive approximations to get our complexity estimations. While first two steps are easily automatable, the last one we leave for reasoning by hand in meta-theory of the specific relation. We are not sure that some general approach, powerful approach, is possible here, because reasoning about complexity often involves arbitrary notions from meta-theory. For example, complexity may depend on length of a list, or diameter of a graph, or number of prime divisors of a number, and so on. So now let's take a brief look at the at how this approach works for our specific example. So here is symbolic scheme for our length calculating query. It's a tree that with different branches corresponding to different disjuncts. One important thing it shows is how grounding is propagated throughout the search. It's denoted here by the overlining, and you can see that in the beginning only the input argument is grounded, but throughout the search other fresh logic variables can become grounded too. Another important thing it shows is these constraints on the edges, on the arrows, which determine whether the search will continue or it halts at this point. Constraints for unifications are just equations of ground terms, and for constraints for relational calls, we use denotational semantics to express them. The symbolic scheme has enough information to apply our compositional formulae and extract these recursive approximations for both our measures. Extracted, they have the form like this. Usually extracted recursive approximations are rather complicated, especially for the scheduling factor, but it's important that they contain all the information about the search, and to solve them you need only to understand logical meaning of the relation. For example, for our example with lists, we can consider two cases of empty and non-empty lists, and we will simplify it greatly, and it would be immediately obvious that the number of transitions for this query depends linearly on the length of a list. Then we do the same for the scheduling factor, but since there is this addition of the number of traces in compositional formulae, we get the different dependency and see that scheduling factor depends it has square dependency to the length of a list. This explains this surprising plot from the beginning. Okay. our measure is able to explain some performance phenomena, but is it applicable for to estimate the overall time of the search in practice? We don't have definitive answer yet, but we suppose that it can, because the scheduling is a detrimental part of the execution in miniKanren. Another important part is unification algorithm, and it can take up to exponential time in worst case, but it's well known that in practice almost always unification requires constant time. That is, if we don't take into consideration accursed check, but and accursed checks are costly in practice, but at the same time they are. It's known that they are rarely violated, so can be safely omitted almost always. There are other parts of miniKanren execution for different versions, and they should be considered on case-to-case basis. For sanity check, we performed an evaluation of our approach for a number of simple examples, and it showed that the scheduling complexity that we derive predicts the the measured overall time quite well, at least the degree of the polynomial. To conclude, here we present a framework to formally define and estimate the scheduling time of interleaving search. This new understanding of nature of scheduling process can help to find new heuristics to construct programs with better performance, and maybe even to modify the search to subdue this overhead of scheduling. For now, our approach has a number of limitations, like the requirements we put on the analyzed program, or the fact that we are only able to analyze the full search, not the search for the first answer, until the first answer is found, for example. So applicability of our approach in practice still requires further investigation, but we hope that this work will be the first step toward the powerful and useful frameworks for complexity analysis in miniKanren. Thank you.